In this video, we're going to look at finding limits as x approaches infinity, positive infinity, or negative infinity. So you see the first activity is to describe the right and left end behavior of the following functions. And as we have discussed in class already, this is kind of revisiting a topic that we've already talked about. When you're trying to find the right end behavior of a function, we've already discussed in class that that's really the same thing as finding the limit as x approaches positive infinity of a function. And if we're finding the left end behavior, that's the same thing as finding the limit as x approaches negative infinity of a function. And although we have introduced it in this course as a calculus concept, this is really a concept that you've looked at in previous courses, and you talked about it as right end behavior and left end behavior. So what you see is a series of six functions, and notice that in all 6 functions, nowhere is there any limit notation or asking for limits. It's simply asking you for the right and left end behaviors of the function. So in the first function, we have an example of a rational function. And hopefully you'll recall from your prior experience that when you graph a rational function, you could possibly have vertical asymptotes, horizontal asymptotes, slant asymptotes, and all of those various asymptotes could have an impact on the end behavior of the function. So in the first example, we have a rational function that is bottom heavy, and what I mean by that is that the degree or the power in the denominator is greater than the degree in the numerator. And you may recall from pre-calculus or algebra 2 that when that is the case, the horizontal asymptote is y equal to 0. Well, if that's the case, then as we go to positive or negative infinity, the function is going to approach its horizontal asymptotes at the ends. Now remember, a function can cross its horizontal asymptotes, but at the ends, the function will approach, in other words, get closer and closer and closer to the horizontal asymptote. So if you wanted to, you could take a look at this function on your calculator to see what it looks like. But in either case, the right end behavior, which is as x approaches positive infinity, the right end behavior will be approaching a y value of 0. And similarly, the left end behavior, as x goes to negative infinity, we're also going to be approaching a y value of 0. Because, as I already stated, on a rational function, the end behavior, a function always approaches its horizontal asymptotes at the ends. All right, let's take a look at number 2. In this case, we have another rational function, but this time the degree in the numerator and the denominator is the same. So to get the equation of the horizontal asymptotes, you will recall it is the quotient of the leading coefficients. So in this case, the horizontal asymptote would be y equal to 3/4, meaning that as we go towards positive infinity, so as x approaches positive infinity, then the right end behavior will be 3/4. We'll be approaching a y value of 3/4. And again, it doesn't matter whether or not the function crosses its horizontal asymptote somewhere in between. At the ends, the function is going to approach its horizontal asymptote. So as x goes to negative infinity, the left end behavior of the function would also be 3/4. And you can graph that, you can verify it with a graph, but again, based on your pre-calculus and algebra 2, these are things that you really already know, you're just kind of reflecting back on. In h of x, we have another rational function, except for this time the function is top-heavy, meaning that the degree in the numerator is greater than the degree in the denominator. In that case, you will recall that there is no horizontal asymptote, but in fact that there is a slant asymptote. To determine the slant asymptote, which is not our focus right now, you would divide the denominator into the numerator, you would do that long division, and you could locate your slant asymptote. But again, that's not really what I'm focused on. What I'm focused on is the fact that if there's a slant asymptote, we know that there's a vertical asymptote here at x equal to negative 1/4, because that's the value of x that makes the denominator 0. So at x equal to negative, here's 1, at x equal to negative 1/4, we have a vertical asymptote. Let's say that the slant asymptote does something like that. Well, when we graph that function, it will do something like that, and I think you can see whenever we have a slant asymptote, the function is going to either shoot off to positive infinity or negative infinity. Whether it shoots to positive infinity or negative infinity is not really that big of a deal, because if the graph is going off to positive infinity or down to negative infinity, we know that the limit does not exist by unbounded behavior. So the right-hand behavior in this case, as x approaches positive infinity, the function is approaching a positive infinity, and if this were a limit question, we would say, well, the limit does not exist by unbounded behavior. And likewise over here, as x approaches negative infinity, the left-hand behavior is approaching negative infinity, and the limit would not exist by unbounded behavior. All right, let's take a look at I of x. 2e to the negative x, you will recall, is the same thing as 2 over e to the x. That's one way to look at it, and that would be a continuous function. E to the x doesn't have any breaks or gaps or holes. You will also recall that instead of being exponential growth, we would have an example of exponential decay. So the graph of 2e to the negative x would look something like that, and we see that the horizontal asymptote of that function is y equal to 0. So the right-hand behavior, as x approaches positive infinity, the function is approaching 0, the horizontal asymptote. But the left-hand behavior, as x approaches negative infinity, the function itself is approaching infinity. So if we were talking about a limit, we would say the limit does not exist because of unbounded behavior. Letter J. Now in letter J, we have what appears to be a rational function, but if we're trying to determine the degree in the numerator is obviously a degree of 1. The degree in the denominator, if you just look at the first term, we basically have the square root of x squared, which is equal to x to the first power. So the degree in the numerator and the denominator is really the same. Therefore, the horizontal asymptote is y equal to the quotient of the leading coefficients. The leading coefficient in the numerator is 1. The leading coefficient in the denominator, now be careful, is the square root of 1, which is 1. So that makes it easy in this case. So the horizontal asymptote is y equal to 1. Therefore, since it's a rational function, actually this is a special case, so let's back up and talk about this one for a second. I wasn't paying attention to the function. So think of the graph or the function like this. The denominator is always going to be positive because we're taking the square root of a number, and the square root of a number, the principal square root, is positive. However, the numerator can be whatever the value of x is. So if we're going to positive infinity, we get a positive. If we're going to negative infinity, we get a negative divided by a positive, which is a negative. So the right-hand behavior would be, as x goes to positive infinity, would be 1. There's that horizontal asymptote. The left-hand behavior, as x goes to negative infinity, would be negative 1, because we're getting negative outputs on the left-hand side. And we'll talk a little bit more about this in class. There are other ways to determine this. You also can take a look, if you want to pull out your graphing calculator, you can see that on the right hand side the function does approach positive 1, and on the left hand side the the function approaches -1. This is kind of a simplistic look at it, and we'll look more closely at that function in class. Finally, k of x is equal to the ln of x. Remember, ln of x has a vertical asymptote at x equal to 0. You can't take the ln of 0. You can't take the ln of a negative number. The function passes through 1, 0. Looks something like that. So the right end behavior would be as x approaches infinity, the function itself approaches infinity. Therefore, if this was a limit, the limit does not exist. Okay, so that's a review of how you would find right and left end behavior when you were in Algebra 2 and Pre-Cal, using graphs, using some of your skills that you developed over time. Finding limits as x approaches positive or negative infinity is the same thing as finding end behavior. A rational function will always approach its horizontal asymptotes as x approaches positive or negative infinity. And I think we saw that in our warm-up in the example. Okay, so now, basically on the next page, we are finding limits. So we're really doing the same thing that we were doing on the other page. Notice I have exactly the same functions, except this time I'm saying find the limit as x approaches positive infinity. In other words, I'm asking you for the right end behavior of this function. And just like we had on the other side, since this rational function is bottom heavy, the horizontal asymptote is y equal to 0. Therefore, the limit is 0, because as we go towards positive infinity, the function is approaching a y value of 0, the horizontal asymptote. In the second example, we're looking for left end behavior because we're going to negative infinity, and the degree in the numerator and denominator is the same. So the horizontal asymptote is the quotient of the leading coefficients, and because this is a rational function, at its ends, the function will approach its horizontal asymptote. So as x goes to negative infinity, the function approaches a y value of 3/4. Next problem, we're looking at right end behavior because we're going towards positive infinity. This is the problem because it's top heavy that had a slant asymptote, and because I have a slant asymptote as x goes to positive infinity, the graph is either going to go off to positive infinity or to negative infinity, depending on the particular function. Now you could think of substituting in a very large number like a million, a billion, to determine whether the output would be positive or negative. Well, let's think about that. If I substitute a billion in for x and I square it and multiply by 3 and subtract 1, I get a very positive number. And in the denominator, if I substitute a billion, 4 times a billion plus 1 is positive, so the outcome's positive. We're approaching infinity, but really, in this case, we're trying to find out about the limit. Since we're approaching infinity, the limit does not exist because of unbounded behavior. Now, in the next problem, I don't have a rational function. I have an exponential function, and we said earlier this is the same thing as the limit as x approaches negative infinity, which is left end behavior, of, I'm going to rewrite this as 2 over e to the x. Now think about substituting a very large negative number in place of x, like negative a billion. If I were to substitute negative a billion in place of x, then that would become 2e to the positive billion, which is getting infinitely large, which tells me that the function approaches positive infinity. Therefore, the limit does not exist because of unbounded behavior. And our graph on the other side verifies that. Remember, we had a graph that was exponential decay, and we said it looked something like that. And so the left end behavior, as I go to negative infinity, the function, the y value, is approaching positive infinity. And again, you could use a very large, or a very negative number, I should say, to substitute and determine that as well. The next function, the limit as x approaches positive infinity, we're looking at the right end behavior. We said that the degree in the numerator and denominator is the same once you take the square root. So we have a horizontal asymptote of the quotient of the leading coefficients. And so if I let x get infinitely large, I'm going to get a positive number in the numerator, a positive number in the denominator. So the limit is x equal to 1. Or I'm sorry, not x equal to, the limit is equal to 1. Now another way to do that is to, and you may have learned this in pre-cal, is to divide everything everywhere by the highest power of x in the denominator. So in this case, the highest power of x in the denominator is x. So if I divide every term everywhere by x, just showing you an alternate strategy. Now you may be wondering why I said I'm going to divide every term by x, but remember, underneath that radical, an x appears as an x squared, because the square root of x squared is x. Alright, and we're still finding the limit as x approaches infinity. So when I clean this up, I have the limit as x approaches infinity of x over x is 1. I'm just cleaning this up. In the denominator, x squared over x squared is 1. And I see that I forgot to divide the 1 by x. So if you come back to this step right here, I should have had 1 over x. You divide every term everywhere by x. So that leaves me down here with a 1 over x. So when I choose a very large number like a billion, and I substitute a billion in place of x, then 1 divided by a billion is approaching 0, because we're dividing 1 into a billion parts, so that's virtually going towards 0. So 0 plus 1 is 1, the square root of 1 is 1, 1 divided by 1 is 1. So that's just another way that you can find the limit as x approaches infinity or negative infinity. And then lastly, we're finding the left end behavior because we're going towards negative infinity. And since we know that the ln graph looks like this, we can't really approach negative infinity on that graph. So basically, there's no left end behavior. So you could say none, you could say whatever. This is not a very valid question because the function itself does not approach negative infinity. Okay, hopefully this has been helpful to think about and consider limits at infinity, and we'll talk more about this in class.